In 1989, George Sebenko proved what's now known as the universal approximation theorem. If we take some complex function, for example this really complicated border in the town of Baarle-Hertog, these parts of the map are in Belgium and these parts are in the Netherlands. The universal approximation theorem guarantees that there exists a two-layer neural network that can fit this border as precisely as we want. A nice way to get a feel for this result is to see what a two-layer network like this does geometrically. Most modern neural networks use some version of rectified linear activation functions. Visually, this means that each neuron in the first layer of our network folds up a copy of our map along a single fold line, where the location of the fold line is controlled by the neuron's learned weights. From here, our first neuron in our second layer takes in these bent planes and multiplies their heights by another learned weight value, which geometrically further bends up or down the folded parts of our planes, and flips over our folded region when that neuron's weight value is negative. These three bent planes are then added together by our neuron, resulting in a surface like this. Our three fold lines from our first layer now divide up our map into these 5 regions, that each become different planes in our second layer's surface. This surface shows the output of our first neuron in our second layer. The second neuron in our second layer flips, scales, and combines our first planes using different learned parameters, resulting in this surface, that again uses the same 5 regions of our map, but at different heights. The height of the surface formed by our first neuron corresponds to the model's confidence in a certain part of the map being in the Netherlands. And the height of the second neuron surface corresponds to the model's confidence in Belgium. Coloring our Netherlands surface blue and our Belgium surface yellow, and bringing these surfaces together onto the same axis, the intersection of our surfaces shows us where our model is equally confident in both countries. This is the model's learned decision boundary, which gives us a basic border separating the core Belgium region from the surrounding Netherlands region.